All right, we should finish chapter 12 today, which will then end all the new material, and we'll review next week for exam 6, and the following week we will review for the final. The final is on Tuesday at 8 o'clock in this room, 8 to 9:50 in here. All right, so mole fraction, again, moles of solute over moles of solution. Remember, to get moles of solution, you're going to add moles of solute plus moles of solvent. All right, so you can't go directly to moles of solution. You have to add the moles of solute and then the moles of solvent. All right, so for a question here, you've got your iodine, which is your solute. You got your methylene chloride, that's your solvent. And even if you didn't know what those compounds were, you have the larger amount is going to be your solvent, the smaller amount is going to be your solute. Again, the mole fractions, you simply take your 5 grams of iodine, divide by the molar mass of iodine, which is 254 grams per mole, if you just give it to 3 sig figs. All right, so that's going to give you your moles of iodine, which is your solute. And then you take your 56 grams of methylene chloride. You get the molar mass of the methylene chloride, 70.9, 14.03, 84.93 grams per mole. You just look that up on the periodic table, and that's going to give you your moles of your methylene chloride. So you simply add those two up, and you will have then your moles of solution. So when you want your mole fraction, you take your moles of your solute, divide by your moles of solution. All right, so here's all the actual answers. They gave 253.8 grams. It's fine. Your final answer is only going to have 3 sig figs anyway, because you started with 3 sig figs. And here again, you're only going to get 3 sig figs because you started with 3 sig figs. All right, so there's your moles of your solute here. And here's your moles of your solvent. So, of course, you have to add those up. When you add those up, you get your moles of solution. So to get your mole fraction, you're going to take your moles of solute, divide by your moles of solution. And if you want the other mole fraction, you simply subtract from 1, or you take your moles of solvent, divide by your moles of solution. Either way will give you the same answer. All right, so you take your moles of the solute over the moles of the solution, and that gives you 0.0290. You then know the mole fraction of your CH2Cl2, because they have to add up to 1. 0.971 is the mole fraction for the solvent. Or you can take your moles, divide by your total moles, and still get that same answer, 0.971. So you can subtract from 1 to get that answer, or do the division, and you will get that exact same answer. All right, so you'll have to know how to get the mole fraction of the solute, the one in lesser amount, and the mole fraction of the solvent. And you also have to know when you add those two mole fractions up, it will add up to 1. All right. All right, so you got a bottle. When you have alcohol and they label it as proof, you divide that by 2, and that gives you your percent alcohol. And now this percent alcohol is by volume, all right, not by mass. When you're doing percent alcohol, it is by volume. And so when you have a 47% by volume, all right, whenever I have a percent, I assume 100 is my sample. This is volume. And so what I'm going to say is I'm going to assume a 100 mil sample. All right, if you had a mass percent, you would assume a 100 gram sample, and everything is grams. When you have a percent by volume, you assume a 100 milliliter sample, and then everything is then converted to milliliters. So that means you have 47 milliliters of alcohol, and the alcohol is ethyl alcohol or ethanol, and then the other 53 milliliters is water. All right, and so you have a 47% by volume of alcohol in water. So you have 47 mils of ethanol, 53 mils of water. That is your 100 mil sample. All right, they give us the density of the ethanol, so we can convert the milliliters of ethanol into grams. We are getting to the mole fraction, so once we get to grams, divide by the molar mass, we have the moles. Water, they don't give us the density, but everyone should know the density. The density is 1 gram per milliliter. To 3 sig figs, it is 1. So we only need 2 sig figs because they only gave us 2 sig figs in the percentage. And then here, they give us the density. We do not know the density of ethyl alcohol. It has to be given. It is 0.80 grams per milliliter. And so you see the milliliters cancel, and you have now converted your volumes into masses. All right, so we have 53 grams of water, but we only it's going to be 5 for 10, 2. All right, so you're going to have 37.6, if I did this ridiculous math right, grams of ethanol. All right, so a 100 mil sample is not 100 grams. It is only 90.6 grams, if I did that math right, but they're going to do the math for me. All right, so once you have the grams, then you simply divide by the molar mass. You simply divide by the molar mass. Here we know it's 18.02 grams per mole. That gives us our moles of water. Molar mass here, you have to calculate it. You got 30.06 and 16, 46.06. So it is 46.06 grams per mole. Once you have the 2 moles, then you just take the moles of your ethanol, which is the lower amount. So the alcohol is the smaller amount of those two. So this is your solute, and then the water is the solvent. Solute, 47 mils, smaller than the solvent, 53 mils. For some reason, they chose a 1,000 mil sample instead of a 100 mil sample. It doesn't matter what you assume. When I have a percent, I always assume 100. And so the percentages turn into milliliters when it's a volume. It turns into grams when it's a mass. But the sample size makes no difference. Any sample size you pick will give you the mole fraction of ethanol to be 0.22 and your mole fraction of water to be 0.78 because they have to add up to 1. All right, so whatever amount of sample you want to pick, I picked 47. They picked, I picked 100 mils sample. They picked 1,000 mil sample. Note that their volumes are adding up to 1,000 mils. Instead of having 47, they have 470. And so my answer is going to be 0.816 moles. And my answer is going to be 2.94 moles. And my addition of that is going to be 3.76 moles. And my mole fraction is going to be 0.816 divided by 3.76, which equals the exact same answer. It doesn't matter what size sample you pick. I pick 100 because it's a percent and it is very simple. All right, little m, extremely useless. If you don't know what this means, then you can never get this problem right. All right, so that is a lowercase m. You have to know that's molality. Even if you know that's molality, that's not good enough. All right, so you know it's molality. And even if you know that that is moles per kilogram, again, that's not good enough. So you have to have the units very precise. You have to know that that means that you have moles of calcium chloride. So we have 3.6 moles of calcium chloride in 1 kilogram of water because it is a solution of calcium chloride. All right, so water is the universal solvent. If it doesn't say that there's some other solvent, it is always water. All right, so we need to find the mole fraction of calcium chloride and water in this solution. All right, so again, to get the mole fraction, well, you got to go to grams and then get moles. Well, you don't have to for calcium chloride because you already have moles of calcium chloride. We have 3.6 moles of calcium chloride. But here, water, we have 1,000 grams. 1 kilogram is 1,000 grams. Just divide that by its molar mass and you get 55.6. I'm not exactly sure if that's what you get, but it's somewhere very close. It's either 55.5 or 55.6. Now that you have your two moles, you add them up, you get your moles of solution. You want the mole fraction, moles of calcium chloride divided by the moles of the solution. So if you know that little m means this is a very easy problem. If you do not know that little m is that, you cannot get it right. It's 55.5. All right, so when you take your 1,000 grams divided by 18.02, it's 55.5. You add them up. This is your moles of solvent here. This is your moles of solution here. Here's your moles of solute here. All right, so you just take your moles of solute divided by moles of solution, and that is your mole fraction of your calcium chloride. When you want the mole fraction of the water, you can subtract from 1, or you take your moles of water and divide by the moles of solution. So once you have the 0.061, you know your answer is going to be 0.939, and Not sure why. Well, this one is 2 sig figs. This one should be 3, whether you're doing it this way or whether you're doing it this way. These questions are hard enough unless you're ridiculous with the sig figs. If it's supposed to be 3 and you have 2, if it's supposed to be 3 and you have 4, you're not going to lose points for sig figs. Getting the answer right is what I'm looking for here. These are hard questions. All right, and even harder is when you are converting molality to molarity, and mole fraction. Okay, so molality and mole fraction, that's pretty easy. When we're doing molality to molarity, that gets much more difficult. So molality and mole fraction, those are simple conversions as long as you know the units of those two concentrations. All right, solution contains this many, this mole fraction of iodine dissolved in that mole fraction of methylene chloride. What is the molality of I2? All right, so again, you have to know the units. We're looking for the molality of I2, which means we need the moles of I2. We need the kilograms of methylene chloride. So the solute, moles of solute, kilograms of solvent. The solvent is your methylene chloride. All right, so we need, and we have this from our mole fraction. All right, and so when you have a percent, you assume 100 grams or 100 mils, depends on if it's percent by mass, percent by volume. If you have a fraction, you will assume that you have 1 mole. All right, so if you have a fraction, I always assume 1 because I know they're going to add up to 1. When I have a percent, I assume 100 because then those percentages turn into grams for mass percent, milliliters for volume percent. All right, so if I have 1 mole, I have 8.89 times 10 to the minus 3 moles of iodine. And I have 0.9911 moles of methylene chloride. All right, so we need moles of iodine. There it is. We just plug that in right there. And now we need to get and convert these moles into kilograms. So you just take the molar mass, 70.9 and 14.3, 84.93 grams per mole. And we don't want grams, we want kilograms. So we have to know that kilogram is 1 times 10 to the third. And then we have our units correct in kilograms. So here we're going to get about, I don't know, about 0.08. All right, so we will get the actual answer when they push the buttons. All right, so they did assume 1 mole. That's what I would definitely do, assume 1 mole. And when you assume 1 mole, you have that many moles of your solute, which is what you needed, and that many moles of your solvent. Molar mass gets you in grams, and now you convert to kilograms. And so now you have your kilograms of your solvent. So you have to have moles of solute, kilograms of solvent. Again, if you don't know the exact units of molality, there is no way you can get this right. All right, this one had 3 sig figs, that one had 4 sig figs. You should give your answer to 3 sig figs, and the molality is 0.106. Again, when you're done, you can just put moles per kilogram, but you need to know that that is moles of I2, and this is what I would like to see, per kilogram of CH2Cl2, because if you don't know that, it is impossible to get that correct. All right, so these are much more difficult, and these are when you are converting your molality to molarity or molarity to molality. In order to do this, you need another number, and that number is the density of the solution. All right, and so again, with density, we did it in experiment 1 in the lab. Density is equal to mass over volume. All right, in this chapter, that is not good enough for the units. When we had our unknown liquid, we weighed the whole thing. We didn't separate it from the water and the alcohol. You didn't know what it was. It was water and alcohol, but you didn't know that. All right, so you didn't separate the water from the alcohol. You took the mass of the whole thing, and so you took the mass of the solution. You didn't separate out the water and the alcohol to get the volume of just the alcohol or volume of just the water. Nope, you took the volume of the whole thing. All right, so you have to know when you're doing density, it is the mass of the whole thing, the solution, divided by the volume of the whole thing. It is solution. Again, mass over volume is not going to be good enough because you might think it's the mass of the solute. It is not. When you have the density, it is the mass of the solution over the volume of the solution. Again, specific units, extremely important. All right, so we have citric acid. All right, we have a 2.331 little m. All right, so again, you don't know what this little m means, you cannot get this right. 2.331 moles of your solute, which is the citric acid, HC6H7O7 per kilogram of your solvent. And this is an aqueous solution, which means it's water. So kilograms of water. All right, so you have to know that is what's given. And they also give us the density of the solution. And so we also know that the density is 1.1346, a heck of a lot of sig figs, grams of the solution divided by the volume of the solution. All right, and now it asks for the molarity of the solution. So molarity, what we're looking for, big M. We need to find moles of solute, which is your citric acid. And now we need the liters of solution. So again, you have to know the specific units for molarity. Moles per liter is not good enough. Moles of solute, liters of solution. All right, we already have the moles of our solute. It is right here. So this numerator is this numerator. We plug that in right there. All right, now for the hard part is to get the volume of the solution. All right. We're going to use the density to get our volume of solution. So we are going to solve for the volume of solution. We're going to get it in milliliters and we will convert it to liters. In order to get to the volume of the solution, we must know the mass of the solution. And so we need to find the mass of solution. So remember, your mass of solution is going to equal your mass of solute plus the mass of solvent. We already have the mass of solvent. It says right here that we have 1 kilogram of water. And so we know that we have 1,000 grams of water. All now we have to do is find the mass of our citric acid. Well, they tell us that we have 2.331 moles of citric acid. All we need to do is go to the periodic table, find the molar mass of our citric acid because they give us the molecular formula, and then multiply that by the moles. And now we have the mass of the solute, we have the mass of the solvent. We add those up, we have our mass of solution. All right, so here are the numbers. So we take the molar mass, you go to the periodic table, you have 8 H's, you have 6 carbons, 7 oxygens, add them up, 192.14 grams per mole. So that gives us 447.88 grams of our citric acid. And we know that we have 1,000 grams of water. So now we have our mass of solution, and it is 1,447.88 grams of solution. All right, but we don't want the mass of solution, we want the volume of solution, and that's why we have the density. So here's our mass of solution and density. We have the grams of solution divided by the milliliters of solution. That is the units for density, mass of solution per volume of solution. So we see that our mass of solution cancels the mass of solution, and then we just have to convert our milliliters to liters. We know M is 1 times 10 to the minus 3. And now we have our volume in liters. And so to get the molarity, we take our moles, 2.331 moles, and divide by the liters of solution, 1.2761 liters. And that is how we get our molarity. And that answer to 4 sig figs is 1.827 moles per liter. So again, this is moles of your solute, which in this case is H, citric acid, HC6H7O7 per liters of solution. Again, I would write out the exact units every time because moles per liter is not very helpful. You have to know it's moles of solute per liter of solution in order to get these consistently right. All right, so now we're going to go the other way. We're going to be given a molarity and a density, and we're going to go to the molality. Again, you have to know that we have 14.1 moles of our solute. In this case, it's the ethanol, C2H5OH, per liter of solution. All right, and the density is given. And the density of this solution is 0.853. And this is grams of solution, not of the alcohol. It is of the solution per milliliter of the solution, not milliliter of water, not milliliter of the solution. So density, you have to know. Mass of solution per volume of solution. Now we are asked for the molality. So what we're looking for is little m, which we need to find moles of our solute, which is C2H5OH. We already have that number. It is 14.1. What we need to find is the kilograms of water. All right, so you have an aqueous solution. All right. So again, to get the mass of the solute, we are going to have a mass of solute plus mass of solvent equals the mass of solution. All right, you're always going to know 2 of these, or you're going to be able to calculate 2 of these and then solve for the third. All right, so we have moles of our solute. All we need to do is find the molar mass of our ethanol. We can easily convert moles into grams, and we would have the mass of the solute. All right, the mass of the solvent, that's what we're looking for to put in our denominator. Of course, our 14.1 goes right into our numerator. All right, so we have 14.1 moles if we have a liter of solution. So then, knowing that we have a liter of solution, we can use the density and find the mass of the solution. All right, again, whenever you're doing this, you're going to find 2 of the masses and solve for the third. In this case, we're going to find the mass of the solvent using the molar mass. We're going to find the mass of the solution because we have a liter of solution and we are given the density of the solution. And once we have this, we take the mass of solution, subtract the mass of the solvent, and then we will, mass of the solute, that would calculate then the mass of our solvent. All right, so here are the numbers. So first we have a 1 liter, so moles per liter of solution. All right, and that's just converting it to milliliters. And then we have our density, grams of solution, milliliter of solution. And so your volume of the solution is going to cancel, and now you have your mass of solution. Then we have our 14.1 moles times the molar mass of your ethanol. And so this is the mass of your ethanol. All right, and so here's your solution. Here is your solute, the ethanol. And so to get the mass of the solvent, of course, when we add our solute plus our solvent, we get the solution. And so we subtract our solution mass minus the solute mass. And then we have a solvent mass. And when we're doing molality, that unit must be in kilograms. So this is kilograms of your water. All right, so now we have finally our denominator. We had the 14.1 moles as our numerator. Now we have found the denominator. Now we divide those two numbers, and we have our answer, an extremely high molality of 69.4 moles per kilogram. And this is moles of your ethanol per kilogram of water. All right, so this is, in this case, your solute, and this is your solvent. And that is because that's how they set up this problem. Now, if you were given this and it said you have 649.7 grams of your solute, in this case it was called solute already, grams of ethanol, which is a liquid, and you have 203.3 grams of water, which is also a liquid. All right. Sometimes we throw out the rules when it comes to water. Water is the universal solvent. We'll always call it the solvent. The rule is when you have two liquids, the one that has a higher amount, this one should have been called our solvent, and the water should have been called our solute. Again, water is the exception to this. Water is the universal solvent, so they always talk about water as the solvent. All right, colligative properties. So colligative properties means the answers that we're going to get for boiling point, freezing point, osmotic pressure, vapor pressure lowering, these four down here, only depend on the concentration. It does not depend on the chemical identity. All right. This is a little misleading because it does depend on ions in solution. Because here it says molecules or ions. All right. And that's where it covers itself, but very unclear. So if we had a 0.10 molal of NaBr, KCl, NaI, KBr, all of these are the same. All of these would be exactly the same. They would have the same boiling point, freezing point. Everything is the same. It doesn't matter that this is sodium and bromine, potassium, chlorine. All right, but note that it is one positive ion, one negative ion. All right, they would not be the same if we had 0.1 mole out as, let's say, you had calcium chloride. All right, or if you had magnesium bromide. All right, so if you had calcium iodide. All right, if you had magnesium fluoride. All right, now all these are the same, but these are not the same. All right, so they all have the same concentration. However, you're looking at the number of ions. When you look at this column here, you see that you have 2 ions in these formulas. You have 1 sodium, 1 bromine, 1 potassium, 1 chloride, 1 sodium, 1 iodine. Right? 2 is the total of ions. So I is the Van Hoff factor. It's the number of ions in solution. Over here, you have an I value of 3 because you have 1 calcium but 2 chlorines, 1 magnesium but 2 bromines, 1 calcium, 2 iodines, 1 magnesium, 2 fluorines. All right, and that would be different than if we had glucose, C6H12O6. If we had 0.10 molal, it is not the same. But you pick any sugar, glucose, fructose, any xylo, any of the things that end in O's, you got all these hundreds of sugars. They will all be exactly the same. But again, that's not the same as the I value of 2 or the I value of 3. These are molecular compounds. These are ionic compounds. So when you talk about ionic compounds, it's the number of ions in solution. Molecular compounds, note it says molecules here. All right, and so in solution is always 1 molecule. And so we still call it I, but it's always 1. Anytime you have a molecular compound, it's not an ion in solution. Note up here, it's molecules or ions. It is 1 molecule. So I, you can say it means ions in solution, but it's ions or it's molecules. If it's molecules, the value is always 1. If it's ions, then it's always more than 1. All right, so we will have these colligative properties: vapor pressure lowering, boiling point elevation, freezing point, I call it freezing point depression, all right, or lowering, and osmotic pressure. So these are the colligative properties we're going to talk about. Again, I can give you a problem and I can pick 10 different sugars and they all have the same concentration. You only have to do it one time. They're all the same. If your I value is 1, your concentration is the same, your answers for boiling point, freezing point, osmotic pressure, vapor pressure lowering, they will all be the same. It doesn't matter what the identity is. It matters what the concentration is and how many ions you have in solution. All right, so the equation that we're going to use for finding the vapor pressure lowering is going to be the mole fraction of your solute. The P with a circle on it, this is pure. All right, so it is a pure solvent. All right, so nothing in the solvent, there's no salt in it, nothing in there. It's pure solvent, nothing in there. There's no solute in there. It's only the solvent. And so that circle means that it is a pure solvent. What you're going to find then is your vapor pressure lowering, how much the vapor pressure goes down. Anytime you add a solute to a solvent, the vapor pressure will always go down. There's no vapor pressure raising. It is always lowering the vapor pressure. All right, so what we need is we need to find the mole fraction of our solute. All right, and so a lot of times they will label that as a B. And then the solvent is an A. So if you see terms A and B, A is going to indicate the solvent, and B is going to indicate the solute. All right, so a lot of times they don't write the whole word. They'll write A and B. They can't put S and S because they both start with S. All right, so A is the solvent and B is the solute. All right, so here is a question. All right. All right, so we're looking for the vapor pressure lowering at 20 degrees Celsius. And here is the solution. We have 8.56 grams of the eugenol, which is C10H12O2, in 50 grams of the ethanol. All right, so here is your solute. Here is your solvent. All right, and so they have to give you the vapor pressure of the alcohol, and if they use a temperature, they're just saying, if I raise the temperature, I'm going to raise my vapor pressure. So the higher your temperature, the higher the vapor pressure. Once you reach a vapor pressure of 760, you're at the boiling point. All right, so the temperatures have to match. They're going to ask for what is the vapor pressure lowering at 20. They have to give you then the vapor pressure at 20. So this is pure ethanol. So the vapor pressure of ethanol, just ethanol, nothing else, at 20 is 44.6 millimeters of mercury. So here is your P naught. That is your pure ethanol. We know that that is 44.6 millimeters of mercury. So now what we have to find is the mole fraction of our solute. So you have your mass. All right, we can convert that to moles by finding the molar mass of eugenol. All right, so we are going to convert that into moles by using molar mass. Same with ethanol. Here is the mass, 50 grams. There's the formula of ethanol. We convert that into moles. Then we add them up. We have the moles of our solution. And so we take moles of the solute divided by moles of solution. Remember, to get moles of solution, you have to add up those two number of moles. You're going to take that mole fraction of your solute, multiply it by your pure solvent to get the vapor pressure lowering. All right, so you take your mass of the solute, divide by the molar mass. This is the moles of your solute. You take the mass of your solvent, divide by the molar mass of the solvent. You have the moles of the solvent. You're going to add those up to get the moles of solution. All right, so once you have your moles of solution, you need your mole fraction of your solute. Here's the moles of solute. Here's the mole solution. You divide those numbers. And so now you have your equation, your vapor pressure lowering. You have to know that that means vapor pressure lowering. So anytime you see delta P, you have to know that that is a vapor pressure lowering, and that is equal to your mole fraction of your solute times the pure vapor pressure of your solvent. So now we have the numbers we need. We have our 0.04581, and we were given the pure vapor pressure, which was 44.6 millimeters of mercury. And then when we push the buttons, we get a delta P of 2.04. All right. So the next question is calculate the vapor pressure of the solution. Sometimes it asks for what's the vapor pressure lowering. The answer is 2.04. Sometimes it asks for what's the vapor pressure of the solution? You have to understand what you're saying when you said a vapor pressure lowering. That means we started at 44.6 and we lowered it by 2.04. So all you have to do is subtract 2.04 from the 44.6, and that will give you a 42.6. All right, when you do a subtraction, it is 1 decimal minus 2 decimals. Your final answer is going to be given to 1 decimal, and when you do that, you get your 42.6. So you have to understand what it means to say a vapor pressure lowering. That is how much the vapor pressure went down from the pure vapor pressure. Anytime you make a solution, the vapor pressure will go down. The pure solvent always has a higher vapor pressure than the solvent with a solute. Once you add the solute, the vapor pressure comes down, and that is called vapor pressure lowering. Oh, well, yes. Okay, so this was with an I value equal to 1. Because if it were sodium chloride, then you would have a different equation. So the better equation is you put an I in there. So I times the mole fraction of your solute times the pure solvent. All right, so if this were sodium chloride, you would have to put the 2 there. If it was calcium chloride, you would have to put the 3 there. This was a molecular compound, and it is a 1. All right, and so that's what the next slide is. Anytime you have molecular compounds, then your I value is always going to be 1. We're not going to deal with that one. All right. All right, so if you have a vapor pressure lowering, that means you're going to have to heat it more to get the vapor pressure to go up, which means you're going to have to heat it more to get it to boil. So you have a boiling point elevation directly proportional, directly related to your vapor pressure lowering. All right, and so here's the equation. Now what I'm going to do is, well, it's a different equation. Okay, here's the equation that you will see. Delta T sub B is equal to I, all right, number of ions in solution. I would always include the I because if it's sodium chloride, you got to put that 2 in there. And then it's Kb, which is a constant, all right, so that is your boiling point elevation constant. And then it is normally C sub little m, which is molality. So m, which is equal to C sub m, which is equal to molality. All right, your delta T sub B, that is your boiling point elevation. Again, you have to understand what you're saying when you say boiling point elevation. The boiling point is higher than the pure solvent. All right, so you have a boiling point elevation. So the boiling point elevation, that is what delta T sub B is. And then K sub B is just a constant. And if you look up water, Kb for water, each solvent's going to have a different constant. Kb is 0.512 degrees Celsius per molal. We have the exact same question for freezing point depression. So here's how they write it. That is not how I write it. Delta T sub F is equal to I Kf C sub m. It's the same equation, but if you're using this one, you must put an I in there because if you're using sucrose, glucose, fructose, you're fine without the I because it's a 1 and it would not change it. But if you're having sodium chloride, calcium chloride, anything that is ionic, then you're going to be off by a factor of 2 or 3 or 4 or whatever the I value is. All right, so same exact thing here, except you need to know that this is a freezing point depression. So when you get this answer, whatever your freezing point is, it is now lower. That's why we throw salt on the icy roads. Then the water doesn't freeze at 0. It freezes at a lower temperature, so it is a liquid. So it melts the ice. It keeps it from freezing at 0 degrees Celsius. It will freeze at a lower temperature. You have a freezing point depression. All right, so your M is the same as C sub M, and that is your molality. All right, again, right at the last time. Again, molality, moles per kilogram, not good enough. Moles of solute, kilograms of solvent. All right, you have to know the exact units for molality. All right, so now we have our equation again, and we're going to solve for the freezing point. All right, so we have eugenol again, and this time, though, we're using diethyl ether. All right, so they give us our molal solution. All right, and these are a couple of molecular compounds. These are organic compounds. And so your I value is 1. These are not ionic compounds. We're not having a metal and a non-metal. All right, these are molecular compounds. All right, what are the freezing points and the boiling points? So in order to find the freezing point and the boiling point, they have to give us the pure freezing point. All right, and so here it is, the freezing point and the boiling point of pure ether, minus 116.3 degrees Celsius, 34.6 degrees Celsius as the boiling point. All right, they also have to give us the constants. So the freezing point, depression, and boiling point elevation constants, that has to be given, or you're going to be given a chart to find them. All right, and so here is your K sub F, freezing point depression constant. Here is your K sub B, your boiling point elevation constant. All right, and so now it's a very, very simple equation because we know it is delta T sub F is equal to I Kf C sub M. And they gave us everything that we needed. All right, and so our delta T sub B is equal to I Kb C sub M. And again, they gave us everything we needed. All right, we have an organic compound. All right, we do not have an ionic compound. It is a molecular organic compound. I value is 1, Kf, 1.79. And then they gave us the molality, which was 0.575 molal. And so you simply multiply those numbers together to get your delta T sub F. Same thing over here, your delta T sub B. 1, because it is a molecular compound, Kb was given, 2.02. The concentration and molality was given, 0.575. And you push the buttons and you get your answer. However, that is not the question. So the question wasn't, what is the freezing point depression? The question wasn't, what's the boiling point elevation? That's what this is. This is the freezing point depression. This is the boiling point elevation. The question was not, what are those? The question was, what are the freezing point and the boiling point? Once you get your freezing point depression, you have to know that you take this freezing point and it goes down by this amount, which is going to be about 1. So instead of freezing at minus 116, it's going to freeze at minus 117. You have to know that the boiling point, which again is going to go up about 1, so this is a boiling point elevation, it is not going to be boiling at 34.6, it's going to be boiling at 35.6. All right, so you have to make sure you're answering the question. All right, and so you have your freezing point depression, 1.03. So if you say that the freezing point is 1.03, you're nowhere close. The freezing point is, it goes down by 1.03, down from the minus 116.3. So now it's minus 117.3. All right, so you have to know that is a freezing point depression. It goes down further, minus 117.3. All right, so when you find your delta T sub B and you say, oh, it's going to boil at 1.16 degrees Celsius, not even close. Delta T sub B means that's how much it's going to go up. The original boiling point was 34.6. Now you add boiling point elevation, it's going to go up by 1.16, 1 decimal, 2 decimals, and so you got a 35.8 degrees Celsius boiling point. All right, so you have to know what delta T sub F means. That is a freezing point depression. It goes down. You have to know what delta T sub B is. It's a boiling point elevation. The boiling point goes up. You have to be given the pure freezing point and the pure boiling point, unless, of course, you're talking about water. So water, you must know. You have a 0 degrees Celsius freezing point, 100 degrees Celsius boiling point. That is something that you have to know. You don't have to know any other freezing and boiling points of any other solvent. You do need to know water. You certainly don't need to know ether. They have to be given. If it is not water, it has to be given. All right. So we do a freezing point depression experiment. The molality of the solution of your 58.1 milligrams of this thing that you've never heard of, which means it's not ionic, it's not on the periodic table, it's not sodium chloride, it's not calcium bromide. What all this tells you is you know that the I value is 1. All right, and then benzene, again, it's not on the periodic table. You know that's a molecular compound. This is going to have to be a molecular compound because like dissolves like. You don't need to know what either of those things are. All right, and so we are going to have a 58.1 milligram of this compound in 5 grams of benzene. All right, so what you then know is here's the molality. All right, now you can't look up the molar mass of this because, well, you can, you just Google it, but all right, we don't have any formula for that. So we're finding a molar mass. And so you have to know that when you find little m, that means you have 0.0784 moles of this per kilogram of benzene. All right, so we know that. And now, how did we get the moles of this? Well, in order to get moles, we took the mass of the anethol and divided by the molar mass of the anethol. And divided that by the kilograms of the benzene. All right, and so that is then how we get our molality. And so what do we know? Well, we know the molality. It was 0.0784. What else do we know? Well, we know the mass of the anethol. We put that in grams, and that is 0.0581 grams. We don't know the molar mass because that's the question. And then the kilograms of benzene, well, we know that. That's 0.00500 kilograms. All right, and so you have this equation where there's only one unknown, and that is the molar mass. And so you simply multiply both sides by molar mass, and then you divide both sides by the 0.0784, and you get the kilograms cancel the kilograms, and in the numerator you have grams, and in the denominator you have moles. When you push those buttons, you have your molar mass. All right. And so then your molar mass is 148 grams per mole. All right, so you have to know how you get moles. To get moles, you're going to take the mass and divide by the molar mass. They do it a different way, and that's fine. You can do it that way. I like to know that how do I find molality? Every time I'm looking for molality, I take the mass of the solute. I divide by the molar mass of the solute. And then I take that and divide by the kilograms of the solvent. All right, and so when the question is what's the molar mass, that means they're going to give me the other three. They're not going to give me the molar mass of the solute. If they're asking for the molality, well, then they're going to give me the mass and the molar mass, and they're going to give you the molar mass. They're going to give you the formula that you can look up the molar mass. All right, here we have 11.2 gram sample of sulfur dissolved in 40 grams of carbon disulfide. The boiling point elevation of the carbon disulfide was found to be 2.63. They gave us our delta T sub B, 2.63. What is the molar mass of the sulfur in the solution? What is the formula of the molecular sulfur? All right, so the boiling point constant, elevation constant for carbon disulfide, Kb, is 2.40. All right, so again, you have your carbon disulfide. All right, anything that's going to start with carbon is organic. Anything that's going to start with carbon, the I value is 1. This is not an ionic compound. 2 nonmetals. You can tell by the name, carbon disulfide. That's how you name a molecular compound. All right, and so you have your delta T sub B is equal to I Kb C sub M. So delta T sub B, they gave it to us, 2.63. The I value, you have to know that that is a molecular compound, and that is not an ionic compound. And so the I value is 1. Kb is given, 2.40. We solve for the molality. All right, and so you will get your molality, and then you have the exact same problem that you had previously. How do you find your molality? Well, you take your mass of your solute, divide by the molar mass of your solute, divided by the kilograms of your solvent. All right, and they give you the mass of your solute. All right, so they give you the mass of your solute. They give you the grams of your solvent, which is easily converted to kilograms. So you have your kilograms of solvent. You're finding your molality from your freezing or your boiling point elevation. So it's exactly the same problem with one extra step. That one extra step is you got to find your molality. In the last problem, they gave you the molality. So the molality is going to be 1.096. All right, and so when you solve for the molar mass, when you put those numbers in, you get a 255.5. That is the molar mass of sulfur. All right, that is not the molar mass of sulfur. The molar mass of sulfur is 32.065. Remember that sulfur is not a monatomic element. When we had our diatomic elements that you had to memorize, there were 7 of them. You had phosphorus, that was P4. You had sulfur, that was S8. And so this sulfur, when you take your molar mass that you calculated to be 255.5 divided by the 32, you now see that there are 8 sulfurs in that molecule. So like we have 7 diatomic elements, we have 1 tetraatomic element, phosphorus, we have one octaatomic element, and that is sulfur. And this problem confirms that the sulfur does have 8 atoms of sulfur in the elemental sulfur. All right, so osmosis. Most of you are familiar with osmosis. You're going to have a solvent flow. The solvent is what's flowing. Your solute does not. Solvent flows, semi-permeable membrane, which means it's going to let the solvent through, not going to let the solute through. All right, and it's going to equalize your concentration. So the concentrations on each side of that semi-permeable membrane are going to be equal. All right, so again, a semi-permeable membrane allows the solvent to pass through, not solute. So it only allows the solvent molecules to go through. All right, so if you have your water, which is, of course, your universal solvent, then you have your glucose. This is going to be your solute. All right, so again, here's your semi-permeable membrane. Only the water can go through. So water is your solvent, and so the water can go through the semi-permeable membrane. Your solute, glucose molecules, or whatever your solute is, not going to be able to pass through your semi-permeable membrane. All right, so if you put water in a beaker and you have a thistle tube and you have a semi-permeable membrane, so you're putting this semi-permeable membrane in this thistle tube, which looks just like a filter funnel. This is the fancy filter funnel. All right, and in this filter funnel that is covered with your semi-permeable membrane, you have a glucose solution. All right, so what is going to go through your membrane is water. All right, and it wants to equalize the concentrations. Well, this is pure water, which has no glucose in it. All right, and so the water is going to continually go into this glucose solution, which is going to push your glucose solution up the thistle tube. All right, and at some point it's going to stop because your pressure is going to keep increasing. As you're pushing this up, you're going to have an increase in pressure. And it will stop when it hits the osmotic pressure. All right, so when your pressure is high enough, then you will get your osmosis to stop, and that is called your osmotic pressure. All right, and so when you reach the equilibrium, it's going to stop once it has reached its osmotic pressure. All right, so your solvent is what is going through your semi-permeable membrane. All right, and so your pi here, this is your osmotic pressure. And we can solve for osmotic pressure and see when that's when your equilibrium is reached. Osmosis stops once you hit your osmotic pressure. And you can solve this osmotic pressure. PV is equal to nRT. All right, except this is not a gas, but the equation works. So if you forget how to do osmotic pressure, just remember the gas law because the units are going to work out exactly the same. So now we're not dealing with gas pressures, osmotic pressures, so we use pi. Then we're going to take moles over liters. That's molarity. So N is moles, volume is liters, and our PV is equal to nRT. All right, and it will depend on how many ions are in solution. So you have your I, then you have your M, which is molarity, moles. We divide this both sides by volume. You have N over V. We're using molarity for that, RT. And so here is your equation for your osmotic pressure. All right, so you have your I value, ions in solution. You're going to calculate the molarity, moles per liter of solution. The R value is the same as it is for the ideal gas law. That's the 0.08206 liter atmosphere per mole Kelvin, which means your temperature has to be in Kelvin. And of course, capital M is moles per liter. And so your pi is your osmotic pressure. That is right here, your osmotic pressure. And when you solve it using this equation, you're going to have units of atmospheres. All right, so there's the equation again, except they continually leave out the I. The I value should be there. All right. If it is just a glucose, any sugar solution, the I value is 1, and it doesn't matter. But if you're doing sodium chloride, calcium chloride, I value will be 2 for sodium chloride. I value will be 3 for calcium chloride. And so it will make a huge difference in your answer to your questions. All right, so we have 21 degrees Celsius, add to 73.15, get that to Kelvin. You have 1 gram of dextran dissolved in 100 mils of solution. 100 mils of solution. And the molar mass is given. AMU I don't use, grams per mole is what I use. All right, and so when you're calculating your osmotic pressure here, pi is equal to, this is a molecular compound, dextran is not, sodium chloride 1. All right, and then we need moles per liter. To get moles, we take our 1.50 grams divided by the molar mass of 4.0 times 10 to the 8th grams per mole per liter of solution, and this is 0.1. That is your molarity, and then your 0.08206, and then your 294 Kelvin. All right, and so you just had to convert your grams into moles and your volume into liters, and then you push the buttons and you get your osmotic pressure. All right, and so your osmotic pressure is 9.05 times 10 to the minus 7 atmospheres. Most of the time you want it in millimeters of mercury, so you multiply by 760. Extremely small osmotic pressure. And that is pretty much the end of chapter 12. There'll be a couple of things we will go through, but we will review next week. No. Did I say Tuesday? Friday. Final is Friday. Did I say Tuesday?
Yeah.
When the hell would I say Tuesday? Final is on Friday, as stated in the syllabus. Yeah, so if you're confused, the final is on Friday. I said Tuesday? Why in the hell would I say Tuesday? The final is on Friday. Yes.